In this session, let's focus on the various tools that are typically used to estimate market risk. The most common tools which we would be discussing in this, one being the value at risk, right? We will be dealing with different mechanisms to go ahead with the value at risk. Then we will look at what is called as estimated or expected shortfall measure, and we will also look at a coherent measure of risk and how these VAR and expected shortfall fit into that criteria also. So we will try to take up a data set and try to work around wherever it is possible, and we'll take a couple of smaller examples also to understand the topic much better. So just to get started with the value at risk part, there are multiple approaches to estimate the value at risk. The major broad categorization being the parametric approach to estimate the VAR, as well as we have the non-parametric approaches. So as we have discussed earlier also, parametric approach is nothing but it involves the data to follow some particular statistical distribution, and based on that probably I may get involved in terms of computation or estimation of some of the parameters like mean, variance, etc. Whereas when we talk about non-parametric, even if the data does not follow any kind of a distribution, I can try to do the assessment of the real, I can do the calculations whatever are required in case of a non-parametric, which means I am not expecting the data to follow any specific distribution, and no specific calculations of mean, median, etc. are required to be done. So the VAR we can estimate through either of these approaches, and in each of these categories again there are multiple methods to go ahead. Out of that, what I am picking up right now is under the non-parametric category, we are looking at the historical simulation approach. So for that, let me take up a small data set to work around, so that you get it becomes more and more clear for you in terms of analysis. All right. So I am taking a simple data set here, which contains the closing prices of Nifty for the last 1 year, right? The closing value of Nifty for the last 1 year. Now, what I typically do in this approach is I try to find out the returns. I may compute the dollar returns or the rupee returns, or I may take the percentage returns. So let's say I am computing the percentage returns on a daily basis. I may take again a continuously compounded set of returns, or a simple arithmetic return, which is either I can take the day 1 value minus day 0 value divided by the day 0 value and call that as an arithmetic return, or I could take the logarithm of day 1 value divided by day 0 value, which can give me the geometric return. To a large extent, if the time periods are very small, both of them will give me similar kind of results. Okay, so these are the returns both on an arithmetic as well as geometric format. And generally what we do is, whatever is the mechanism we have computed the returns, we arrange the returns in an ascending order. Just after the returns are computed, what I'll do is I'll take them onto a separate sheet. I arrange the returns in the ascending order. Okay, I'm sorting the data and taking it in the ascending order. So let me do it again. I arrange the data in the ascending order. So this is the order in which the data is arranged. Now how many records are there? Probably if I go to the last, there are 250 records or 249 records. So when I am arranging the data in the ascending order, now I may be interested in finding out what is my 1% var or what is my 5% value at risk. So all that we are doing is identifying the 1% of the entire data. So in this, as we are seeing, if there are n observations, or probably how am I computing the var in historical simulation approach, the observation which separates the tail from the rest of the data. So for n observations with a significance level of alpha, the var is alpha into n plus 1 observation. So if I want 1% var, the alpha is 1. So all I am doing is alpha into n plus 1th observation. So alpha is 1% into n is 250 observations plus 1th observation. So it's almost 3.5th observation is what is we are taking as the var. Sometimes nowadays we are even seeing that plus 1 is not there. So we are taking the 2.5th observation itself as the var rather than the 3.5th. I mean, in some books we have it mentioned as 3.5th observation, whereas in some of them it would be mentioned as 2.5th observation itself. So whatever it is, if we are talking about the 2.5th, okay, this I know as the second observation, this is the third observation. So I can take the linear interpolation between these two and I say that this particular data, so 2.5 is nothing but the average between these two. So I could very well say that my 1% var is around minus 3.67 percentage. Convert this into percentage and probably I can say that my 1% daily var is, though the value comes out as minus 3.68, the usage term is 3.68%. We ignore the negative sign and we try to present it. So what does that mean? There is a 1% chance, there is only a 1% chance that I will lose more than 3.68% on Nifty in one single day. There is only 1% chance of losing more than 3.68% on Nifty on one single day. Similarly, when I am talking about 5% var, we can talk about 5% into 250. So 12.5th observation. So I have, this is my 12th observation and this is my 13th observation. That gives me the 12.5th. So I can very clearly make out that there is a 5% chance of losing more than 1.78% on Nifty in one single day, which means out of every 100 days, in 5 days I can expect the Nifty to fall beyond 1.78%, whereas in one day out of every 100 days I expect the Nifty to fall even beyond 3.68% on a single day. That is what is the var explaining for us. So some of the major considerations, how can I make those kind of things, how can I take the historical calculation to the future decision. So for that what we are saying is all those statements whatever I am making are valid only if I am expecting that the future returns follow the similar patterns as the past. So if the future behavior is more or less on the similar terms as the past experience, then I can very well expect that the loss may not be more than this particular number in future. One thing is probably if the economy is going to change drastically in future, or the investment situations or the scenarios change, all these things don't get captured as a part of the historical simulation approach. And as we have clearly identified, this is one of the easiest methods to compute VAR, because once the data is arranged, there is nothing else that needs to be done. It's only picking up the alpha percentage of the total number of records, and based on that identifying that as the VAR, which separates the 5% or 1% of the data from the remainder of the data. Alright. Then we have a few parametric estimation approaches. But as we have seen, when I say parametric estimation, we need to know the distribution of the underlying data. So if we see here, okay, these are the returns, right? I can find out whether these returns are following a normal or a non-normal distribution. How do I find out? If the skewness is 0 and the kurtosis, excess kurtosis is 0, I can say the distribution is a normal distribution. So when I have tried finding out the skewness, it is very close to 0, and when I tried finding out the excess kurtosis, this is not close to 0, it is slightly more than 0. So this distribution as such may not be a full normal distribution, but it may so happen that when I remove one or two outliers from this data, so probably I will try to find out let's say a maximum value in this. Just giving you a very quick insight into it, 3.73. So if I remove that 3.73 or the maximum 1, 2 values, let's say I simply delete them, it may so happen that you see the kurtosis has come down, but not so heavily. So what we can do is sometimes by removing couple of values and all, we may bring it into a normal distribution. But if at all this is so what we are saying is, whenever I have to estimate the VAR using a parametric approach, the first thing is we need to establish the distribution of the underlying data. We need to know what distribution the data is following. In general, what we may see is the prices. Prices we generally check out for they following log normal distribution, whereas the returns we generally assume that they follow a kind of a normal distribution. So in this example, if I assume that the returns, whatever is the method, the arithmetic or geometric, generally if I am taking arithmetic returns, it follows a log normal distribution. What I can say is the VAR, right? Returns follow a normal distribution. So what do I take as a VAR? Let's say I want 1% VAR. For that, first thing I need to find out what is the mean. If I am going with a parametric approach, I have to find out the mean. I have to find out the standard deviation. Okay. So what is the mean of the return, assuming that this is already normal, though we have found that the skewness is 0 but kurtosis is not close to 0. I am assuming that this distribution is normal, and based on that, okay, this is the mean and this is the standard deviation. This is the mean, this is the standard deviation of the returns. So the 1% VAR is nothing but the mean minus 2.33 times the standard deviation. The mean minus 2.33 times the standard deviation, and the negative of that, that's the reason we get, instead of what we have written in the Excel formula was mean minus the Z for 1% is 2.33 times the standard deviation, and this will be a negative value, but we will take the positive, which means the minus of this is what we take as the var. So basically this is working out to the var is around so there is a 1% chance that the loss will be more than 2.6%, which is much lesser than what is predicted by my non-parametric historical simulation approach. Similarly, in case of 5% var also, it becomes mean minus 1.645 times. If I am going for a 5% var, I am primarily looking out for 5% in the left tail of a normal distribution. So 1.645 times the standard deviation. So this is working out to somewhere around 1.8%, which is more or less consistent with the 5% var that is given by the historical simulation approach also, whereas the 1% var, there is a difference between the two approaches. Alright. So what we are simply saying is that mechanism can very robustly be used only if we see that the returns are following a normal distribution, or probably the prices are following a log normal kind of a distribution. Sometimes, so if at all we are talking about the price yesterday, we can multiply this return whatever it is. So the last day's price is 6363.9, right? The last day's price is 6363.9. So what I could easily say is 1% var is 6363.9 into whatever we have got as the var. What is the var we have got? This much. 1% var was this much. Probably I should take the negative of that. So there is a 1% chance that I will lose more than 166 tomorrow. There is only 1% chance that my loss will be more than 166 tomorrow. But if I am assuming instead of arithmetic returns, the geometric returns are following a log normal distribution. Assume that these are geometric returns only. Then the var, how do I compute the 1% var? I will raise whatever I have got, this number, I will raise it to the power of this. I will raise e to the power of this, and I do 1 minus of this. So probably it is like 2.57. If at all I am talking of this, these returns, if they are arithmetic returns, I will say that my 1% var is this much. If these returns are geometric returns, I will do the same thing until here. I will compute the 1%, I will compute mu minus 2.33 times the sigma. But that amount I will raise it to the e power and subtract that number from 1. So this will give me a slightly different number, 2.58%. So if I am talking about the same 6363.9, I multiply it with this, saying there is a 1% chance of losing more than 163.9 in one single day, if at all these returns were geometric returns. If these returns were arithmetic returns, then probably I can say there is a 1% loss chance of losing more than 166 rupees tomorrow based on the current price. Whereas if I am expressing it in percentage, the 1% VAR is 2.6% of the value. So that way we can estimate the value at risk using the parametric approaches. And both if the time periods are very, very small, whether I take the normal returns or whether I take the arithmetic returns or geometric return, both of them will lead to more or less similar kind of result, and the VAR may not be that exceptionally different for smaller time periods. But the only biggest problem with the VAR is, if we see here, it is saying that yes, I can lose beyond more than 166 rupees in one single day. But it does not talk about how much would I lose. It is only putting a borderline, saying there is 1% chance of losing more than 166 rupees in one single day. But it's not saying more than 166 means how much. It could be 300, it could be 500, or it could be 200, or it could be 1000 also. So that is not given by the typical value at risk kind of calculation. That's the biggest drawback of value at risk calculation. But at least it gives an indication of a borderline. Beyond this, the chances of losing are very, very slim. So that way it can help us in doing comparisons more and more effectively. Alright. Then, so to address that problem, we are getting into a mechanism called expected shortfall mechanism, which is more like, okay, if I want to put it slightly in a diagrammatic form, we know that okay, this is the VAR. Okay, this is the 5% area, right? This is the 5% area, and this is what is the point that separates the 5% from the remaining 95% of the area. So there is a 5% chance of losing beyond this. Similarly, okay, I can find out there is a 4% chance of losing beyond this. There is a 3% chance of losing beyond this. There is a 2% chance of losing beyond this. There is a 1% chance of losing beyond this. So what it is finally coming out is, if I take the weighted average of all these things, if I take the weighted average of all these things, that is what is nothing but the expected shortfall. I take the VARs for different confidence levels. So instead of 95% confidence level, which is nothing but 5% VAR, I will also find out the 96%, which is nothing but 4% VAR. Like that, I compute the VARs at different levels of confidence or different levels of significance, and I take the average of all of them. That is what is taking me to the expected shortfall. So just to give a simple illustration, let's say if I am going with 1% VAR, 2% VAR, 3% VAR, 4% VAR, and 5% VAR. What are these? This 5% VAR is nothing but the mean minus, how do I, or mean plus, I'll directly use the norms inverse, norm S inverse, the 5%. If I take this multiplied by the standard deviation, I'm getting the same 1.833. This is probably I multiply this entire thing by 63.9, which is the yesterday's closing price. Okay, 63.9. So there is almost a 5% chance of losing beyond 116 bucks. Okay, there is a 5% chance of losing. So if I am taking it something like this, there is a 1% chance of losing more than 165.78. There is a 2% chance of losing more than 146. There is a 3% chance of losing more than 133, 4% chance of losing more than 124, and 5% chance of losing 116. Either I take the average of all these numbers or a weighted average of all these numbers, right? Probably this is equivalent to a 99% confidence interval, and this is equivalent to a 98% confidence interval, and so on, right? Either I can take the weighted average of all these numbers and say that this is my expected shortfall, or even probably if I am taking a plain average of these numbers, it is coming out to somewhere around 137.31 rupees. Means the average loss, the expected loss on this particular security is going to be 137.31. Or probably if I am doing a weighted average, I could very well go with a weighted average mechanism, which is okay, I am very well, probably I am doing a multiplication of that and I am doing a summation of these things. Okay, this is coming out to somewhere around 129. The weighted average mechanism is coming out to somewhere around 129. And sometimes people also have gone ahead with by giving the weights in this manner, 1 by 1 minus alpha. So if the weights are given more like this, 1 by 1 minus alpha kind of weightages to each one of them, let's say these are the way the weightages are being given. So it is even resulting in something like this, right? This multiplied by this, and then I am dividing by the summation of this. Even some such kind of mechanisms are also being put, 137.06 being the weighted average of this particular exercise, saying the expected shortfall is to the extent of 137. So depending on how many such VARs I am computing, sometimes I can very well go with very small minute intervals. Instead of just 5 spacing intervals, I could think of 1000 spacing intervals and compute all the VARs and take the weightages like this, and then arrive at the weighted average, saying that that is the expected shortfall. So the conceptually what we are trying to do is, we are trying to find out the expected or the average tail loss. Instead of saying this is the border point, we are trying to do the average of the various border points and try to arrive at one single number, which is saying this could be the average loss for me from this particular transaction. So as the number of intervals are increasing, probably whatever is the expected loss that is coming out with the weighted average mechanism, it may very closely approach the actual value also. Alright? Okay. Then we are also looking at Another such kind of a measure, which is a very generic kind of a mechanism called as a coherent risk measure. All we are saying is instead of looking at only the tail, which was done by, instead of looking at only the tail and breaking the tail into equal parts and doing a weighted average as done by the expected shortfall method, what we are saying is, if this is my loss distribution, try to divide this entire area into various quantiles and find out the VARs for each one of them, and assign the weights to each one of them, and finally do a weighted average of all these values to arrive at very generic measure of risk, out of which the expected shortfall is a special case, which is giving a weightage of 0 to all these measures, and a weightage of 1 by alpha. It's not 1 by 1 minus alpha, we are giving, let's say 1 by alpha. Instead of 1 by 1 minus alpha, let's say I give a weightage of 1 by alpha to each one of them. Okay, so 1 by alpha weightage is given to each one of them. Finally, this is coming out to be my VAR as 147.94. So probably instead of taking the weightages across the entire loss distribution, I only consider the tail losses. For each of the tail loss, I give 1 by alpha as the weightage, and for all these things I am giving a weightage of 0, and that is what is nothing but expected shortfall. Whereas when I am looking at VAR, whatever is the boundary point, the whole weightage is given only to that boundary point, and rest of them are given the weightages of 0, even this side as well as this side. So that's where we say, in a coherent risk measure, the simple thing is, for the entire loss distribution, I am breaking it into quantiles. I am finding out the value corresponding to each of the quantiles, assigning weights to each of the quantiles, and doing a weighted average to arrive at the amount that is at risk, which is what we call as the coherent risk measure. And we are also saying the two other measures which we have done, the expected shortfall as well as value at risk, both of them happen to be the special cases of coherent risk measure itself. In case of value at risk, it is simple, only that particular border amount I am giving the entire weightage of 1, whereas rest all towards the tail as well as towards the other side, both of them are being given a weightage of 0. So that is where the VAR is being arrived at. Whereas when I am talking about the other measure, which is expected shortfall, at least to the right of the distribution, the weightages are given as 0. Whereas towards the tail, we are giving a weightage of 1 by alpha to each of the tail loss, and finally computing the weighted average of all the weights, giving all the weights, which is what is resulting in an expected shortfall. And it is more and more sensitive to the number of quantiles. The more I am increasing the number of quantiles, the more and more convergence to the actual risk happens in the coherent risk measure. Then the other important concept in this particular chapter is, how do I estimate the standard error of this coherent risk measure, right? How do I measure, because the precision or the accuracy of any estimate will be very heavily dependent on the standard error. the lesser the standard error, the high is the reliability or the precision of that particular measure, right? So what we are saying is, we are typically looking at not just one single measure for the R, but the interval for that particular var based on some level of confidence. Okay, right now if I compute the var, I got it as, let's say, 150. My 5% var is 150. Now my interest is find out a 95% or probably a 90% confidence interval for this var. So the 90% confidence interval for this var probably may be between 120 to 180. Means I am 90% confident that the 5% var will lie between 120 to 180. So this is what we are calling as the confidence interval of the coherent risk measure. So 150 is the actual value, but depending on the confidence interval, so when I am going with a 95% confidence interval, so probably it may come out as 150 plus or minus 1.645 times the standard error of the coherent risk measure, whatever it is. So the standard error, once I am able to compute it, that is what will determine what is the 90% or 95% confidence interval for my estimate. So for the standard error, we require this particular formula. If at all I have to find out the standard error, all we are saying is the probability to the left of the distribution into the probability to the right of the distribution by n, that is divided by f of q, which is nothing but what is the area between the range. So we'll take one simple example. Now let's say I want to find, okay, let me take one example. For a 95% confidence interval var, right, 95% confidence interval var. So what is the value corresponding to 95% confidence interval or 5% var as a part of my normal distribution framework? The 5% var, this is having 1.645 standard deviations, right? So probably I can round it up to 1.65. Now I will also assume a bin width interval around it. Means, okay, as long as this is lying within this interval. So I will take an interval, because we are talking about a coherent risk measure. We are looking at the blocks of values or probably the different quantiles rather than one single value. So if I assume that this quantile width is around 0.1, the width of this particular quantile is 0.1. So basically I want my var to lie between 1.7 and 1.6 standard deviations to the left of the mean. So all that I require is, okay, if I take this as the mean, this becomes 1.7 standard deviations and this becomes 1.6 standard deviations, and probably this is my Q, which is my 95% var level, which is 1.65. So because it is 1.65, I am more interested in a bin width of 0.1 I'm looking at it lying between 1.6 and 1.7. Right, it's nothing but 1.65 plus or minus the bin width by 2. So it is giving me 1.6 to 1.7. So I'll try to find out what is this area which is less than minus 1.7. What is this area which is greater than minus 1.6. So how do I find out in a normal distribution? I can take it from the tables. So I will take out from the normal distribution, standard normal distribution. So z value is minus 1.7. If I am taking my z value, okay, I take my z value as minus 1.7, which is giving me that the area is 0.0445, and the same way I want to the right side of the distribution more than 1.6. So the left side will be given, so I will do the 1 minus of that to get the right side. So I will take it as minus 1.6 with a cumulative. So this is telling me 94.52. So in our standard error language, this is called as P, right? And if I want to find out f of q or f of q, which is nothing but the area that is in between minus 1.7 to minus 1.6. So this is nothing but the difference between these two areas, right, which is around 0.10. So if at all I have to find out the standard error, I will talk about the p into 1 minus p by n. Okay, p into 1 minus p by n. This is based on the sample size. If I assume that my sample size is somewhere around 100, so p into 1 minus p by n, let's say, is that. So I will divide the, I will take the square root of this in the first step, okay, and I will also divide by f of q. The f of q for me is nothing but this one. So the standard error comes out to be somewhere around this. So what will I do? To compute my var, I will take what is my original var, right, whatever was the original var, I will take it as I will take, first of all I need to find out that the var of q or the area lying between whatever is the q minus 1.645 minus 1.645 plus, I want the 90% interval for this estimate, or let's say 95% interval for this estimate. So if I want 95% interval, I am taking this as 1.96 times the standard error, this much, and the same way I will take minus 1.645 times 645 plus 1.96 or probably minus 1.96 times the standard error. So I want the value, so probably instead of taking minus 1.645, I will consider directly 1.645 itself. So this is giving me that the 95% confidence interval for me 1.645. So it is giving me that the 95% confidence interval for the same, when I am going with a standard error with 100 elements. But if I am going with a standard error, let's say with a sample size of 500 instead of 100, probably this number is coming down more and more comfortably. So as the sample size is increasing, my var interval is actually coming down. But if the sample size is much lesser, the var interval is actually more and more. So what we are trying to find is not just one single estimate of var, but a typical interval. So basically going with this formula also, if the sample size is large, n is large, so what you will find, the standard error will come down, which means the interval will become more and more narrower. Similarly, if the bin size is very large, the f of q will become much higher. So if the f of q becomes much higher, probably the error will come down, and again the same thing, the narrower will be the interval. So what you can do is the same exercise has to be done separately for each quantile, which requires intensive computer programming and calculation. So that is the way we have to model what could be the 95% or 90% confidence interval of value at risk in each of these particular quantiles. Alright. Then how do I check out whether my data is following a normal distribution or not? For that we take the help of QQ plot. QQ plot, what we typically do is we take the actual data, right? Probably in this itself, this is the actual data, right? And what I can also take is, what if these returns follow a normal distribution? So these are the actual returns, right? What if these returns follow normal distribution? What should be the corresponding values? Let's say if they are following a normal distribution. So if I am saying that they are following a standard normal distribution, what I could take, or probably I'll take the inverse. If they are following a standard normal distribution, I'll take what is the value corresponding to probably see they are they are in the first, second, some such kind of positions, right? So if I look at these being the positions, and if I say okay, norms inverse, the probability side, if I simply put this divided by the total, the counting of all these numbers. So if at all this is following a normal distribution, probably this particular value should be around minus 0.026. The same way I can create, if at all this is following a normal distribution, this is following if this entire distribution is following a normal distribution, probably these should be my expected returns. So what I can do a simple plotting between these two things. Okay, I will insert a kind of a scatter plot between these two things. This kind of a plot wherein you will take the actual values on one axis and expected values if it follows a specific distribution on the other axis. And if you see that majority of the points are along the 45-degree line, we can very well say that the actual data is fitting the distribution. But if the majority of the points deviate from that, then we say that the data does not follow a kind of the expected distribution. So this is how we can compute, and what we are typically seeing in this case is probably in the whole of the middle there is a kind of an overlap with the 45-degree line, but somewhere towards the last on either of the sides we are seeing that the expected distribution is nowhere slightly differing from the actuals. So in the tails probably it is not following the normal distribution. The same way I can test it out with the t distribution or some such kind of distribution and come out with this QQ plot. This is what we call as a quintile plot, because we are trying to map each of the values of this with the values of the other. Pairwise kind of a mapping is what we are trying to do in this. So this empirically creates a kind of an understanding whether the data is fitting the hypothesized distribution or not. So the graph would be linear if both the distributions are more or less the same, but it's not a statistical test. Please try to understand, it's more of a graphical view. Most of the points lying along that straight line we can very well conclude that our data is fitting that particular distribution. So there is no statistical test, no hypothesis testing involved with this process. It's more of data visualization only. Alright. So that's how we use the various mechanisms to compute the value at risk, either using parametric as well as non-parametric mechanisms. We have a mechanism of computing the expected shortfall and even a coherent risk measure, and also getting into the computation of the standard error of the coherent risk measure. I hope all these things are comfortable for you from a conceptual standpoint. If you have any further clarifications regarding any of these things, I suggest that you can get back to me by giving me a call on this number, or even you can email me at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.